Hello everyone, I welcome you all at Infinity Codex, and our today's topic is what is normal distribution. In this, we are going to study what is standard normal distribution versus normal distribution, what do we mean by kurtosis, and what is empirical rule. Before understanding all these important topics, let us see the two most important terms which are related to the normal distribution. First is mean. Mean is nothing but the summation of all the values divided by total number of values. Here our mean is 450 divided by 9, that is 50. Then there is standard deviation. The formula for standard deviation is sigma is equals to under the root of summation of I is equals to 1 till n xi minus mu, that is our mean, divided by 2. And our standard deviation here is 25.8. Now, wait a minute. What is standard deviation? Standard deviation is the measure of dispersion of a dataset from its mean. Now, let us see what do we mean by normal distribution. Normal distribution is a bell-shaped curve, which is also called as Gaussian distribution. The idea behind this function is that the data near the mean occurs more frequently than the data away from the mean. It means that data around the mean represents the entire dataset. Most of the data points lies close to the mean and tail will be symmetrical in both the direction. The formula for normal distribution is this. The graph of the normal distribution depend upon the two main factors. First, mean, and second, standard deviation. These both are also called as parameter of distributions. You will many times see notations such as this, x, mu, sigma. Now this notation means x follows normal distribution where mu is certain value and standard deviation is certain value. Now you will ask, what is the use of parameters of distribution? Here, the mu determines the location of our graph and standard deviation sigma determines the height of our graph. If standard deviation is normal, the graph will look something like this, perfectly distributed. If standard deviation is low, graph will look something like this, tall and narrow. If standard deviation is high, then graph will look something like this, short and wide. Here we can see the perfect example of how change in standard deviation with constant mean leads to us different types of graph. For example, standard deviation is equals to 9 leads us towards the tall and narrow graph. Standard deviation with 36 give us normally distributed graph, and standard deviation of 100 give us short and wide graph. Many times you have heard the term standard normal distribution and normal distribution, but what is the exact difference between both of them? In standard normal distribution, we have mean is equals to 0 and standard deviation is equals to 1, where in normal distribution, we have different value for one or both of those parameters. Sometimes we convert normally distributed data into standard normal distribution. Any normal distribution can be transformed into standard normal distribution to calculate area between and beyond x values. Z-score converts x values into standard values. Here, z value is the distance of the x from the mean in number of steps, that is standard deviation. For example, we do standard scalar to scale our data. Let us see the implementation of Z-score with an example. Here the question is, what percentage of military student will survive up to 480 hours of intense training, where mean is 300 hours and standard deviation is 90 hours. As we know, the formula of Z-score is equals to x minus mean divided by standard deviation. So we put values in the formula, that is 480 minus 300 divided by 90, that is 2. For z is equals to 2, shaded area is 0.9772. Thus, probability of student will fail is 97.72%. relatively is 1 minus 0.9772 is equals to 0.0228. That is, 97.72 students will fail up to 480 hours of intense military training and only 2.28% will clear the training. Now, let us see what is kurtosis. Kurtosis measures the peakedness of distribution. In this, we will study axis kurtosis. The axis kurtosis is used in statistics and probability theory to compare the kurtosis coefficient with the normal distribution. Axis kurtosis can be positive, that is leptokurtic distribution, negative, that is platykurtic distribution, or near to zero, that is mesokurtic distribution. Since normal distribution have a kurtosis of 3, axis kurtosis is calculated by subtracting kurtosis by 3. Leptokurtic distribution. In this, kurtosis is greater than 3, which is also called as positive kurtosis. Leptokurtic is having very long and skinny tail, which means there are more chance of outliers. Positive values of kurtosis indicates the distribution is peaked and possess thick tail. An extreme positive kurtosis indicates a distribution where more of the number are located in the tail of the distribution instead around the mean. Mesokurtic distribution where kurtosis is almost equals to 0, which is also called as normal distribution. Mesokurtic is the same as the normal distribution, which means the kurtosis is near to 0. In mesokurtic, distribution are moderate in breadth and curves are a medium peaked height. Platykurtic distribution where kurtosis is smaller than 3, which is also called as negative kurtosis. Platykurtic have a lower tail and stretch around the center. Tail means most of the data points are pressed in high proximity with mean. A platykurtic distribution is flatter, less peaked when compared with the normal distribution. Now we will see empirical rule, which is also called as 68%, 95% and 99.7% rule. This rule states that 68% of our data values will lies in first standard deviation, that is from mu minus sigma till mu plus sigma. Then 95% of our data values will lies in second standard deviation, that is from mu minus 2 sigma till mu plus 2 sigma. And finally, it states that 99.7% of our data values will lie in third standard deviation, that is from mu minus 3 sigma till mu plus 3 sigma. Any value which is lower or above the third standard deviation value is usually considered as an outlier. This is it for this video, guys. Thanks, and I will see you at the next lecture.